So today we shall continue with message authentication codes. Okay, so or which is also popularly called MACs in cryptographic literature. So we will address certain topics in MACs, although the topic is quite vast. So we will study what are the security notions of MACs, and then follow that up with something which is called NMACs and HMACs, and conclude with something which is called CBC-MAC. Okay, so these are some MAC construction techniques which are there. So in the last class actually we had seen that we have studied about unkeyed hash functions. Okay, so unkeyed hash functions which are of iterative type, and the construction algorithm was known as Markle-Damgard construction. Okay, so we have also seen that it was not easy to extend this to a keyed hash function because of certain pitfalls, right? Because of the iterative nature, I mean, given one message and its corresponding MAC, we were able to find out the another message's corresponding MAC without knowing the key value. Okay. So therefore, this is the Markle-Damgard construction. If you remember that what we thought of is that if we want to convert this into a keyed hash function, then a simple methodology would be to replace this IV, starting technique would be to replace this IV with a key value. Okay. But that has the problem. Why? Because of the iterative nature. If you know that if I append this message or prepend this message, then I can actually predict the corresponding MAC value without necessarily knowing the key value. Okay. So and it is quite easily possible. Okay. So therefore, so what are MACs? MACs are actually message authentication codes, and they are keyed hash functions, and we have seen where are the applications of MACs. So MACs were used. One of the very important usage of MACs was data integrity. That is, given a message, if I am interested in to assure the integrity of the data, okay, and also authenticity, then I use MACs. Okay. So one possible construction could be to make the IV or the initialization vector of hash functions secret. So initially, I mean, in case of unkeyed hash functions, your IV value is a public value. Okay. So everybody knows the IV value. So one starting technique or what comes to our mind is to just replace that IV by a secret IV, and then the idea is that only the sender and the receiver knows the IV value. Okay, and knows the key value. Okay, but there are problems. Why? Now because we have seen that constructing MAC by making IV secret does not work. Okay, so we will again just revise this. That is, consider for simplicity a hash function which has got no pre-processing step. So you know what is a pre-processing step now, that is, given a x values, from there I make a y values, so that it is a multiple of a fixed integer. Okay. So pre-decided block size. So with no it does not have this pre-processing step, and there is also no final output transformation. So there was one optional transformation, and suppose that is this optional transformation is missing in the MAC construction. Okay. So thus every input message is a multiple of t, where compress is an m plus t to m bit, m plus t bit to m bit transformation, and assume that the key is also of m bits. Okay. So therefore the so you see that the key is of m bits, and your initial message which you start with is of size t bits. So therefore you can actually append them and apply the compress function. From there you obtain an m bit digest, take this m bit digest and again take the next block of t bits, again apply the compress function, and you can do it repeatedly, right. So you see that you can actually continue in this way, and from there you can construct given x, you can construct hkx. Okay. So but the problem is that given x and given hkx, that is, suppose the adversary has this knowledge, that is, he knows the corresponding message and he also knows the corresponding MAC value. So can he efficiently determine another valid pair? That is a question. Okay. So that means another x dash value which is not equal to x, and correspondingly another hkx dash value which is also forms a valid pair. Okay. So but note that the attacker does not know the value of the key, right. The attacker is unaware of the value of the key, and he has to do this quite efficiently. So it is quite easily possible, and we have just seen it. So therefore again I will revise it. So hkx is nothing but complex of k comma x. Okay. So therefore you take k and you take x. What is the size of kx? It is m plus t bit. So therefore you see that from this, if you apply the compress function, you can obtain an m bit output which is an hkx value. So, now if you consider another message pair or message which is say x appended by x dash. So, then assume that x and x dash are both of t bits, okay, that we have assumed already. So, in that case what will be the value of the corresponding MAC of x appended with x dash? It will be compress, but compress will now be applied over hkx and x dash, right. Do you see that? Because how will you do this compute this MAC value? You will first of all take x and then append this with the k value or prepend this with the k value and apply the compress function, right. So, from there you obtain hkx and again take the next x dash value and apply the compress function, right. So, this way actually you see that in the right hand side you know already the value of hkx and you also know the value of x dash. Okay. So, therefore, compress being an unkeyed operation, you can easily compute this corresponding output and from there you can obtain the value of hkx appended with x dash. Okay. So, you see that here the attacker has not used the knowledge of the key at all. Okay. What he has used is a previous MAC computation, right. So, therefore, given this construction, it is clear that this is not so good, right. So, therefore, so which can always be computed even though the key is secret, and this can also be attacked to I mean this can also be applied actually to those cases where padding is required and there is a pre-processing step. So, you can actually easily extend this to those cases where padding is there and also where there is a pre-processing step. So, padding is there in the sense that x is not actually a multiple of a fixed block length say t, okay. And then what you have to do is that we have seen in the MD5 and SHA-1 construction, what do we do? We actually appended them with certain length, some predefined vectors like say zeros or 1 followed with zeros and made them a multiple of a particular block length, and then we also added the length of the message, right. That is the 60, for example, in SHA-1 we appended that with a 64 bit representation of the decimal value of the length. Okay. So, such type of steps can be there and still this attack will hold. Okay. So, let us see. So, suppose let us consider a hash which has got a pre-processing step. So, therefore, y is x appended with the pad of x. Okay. So, pad can be some arbitrary function, we are not going to the definition of pad, but it can be something, right. But we have seen that there are certain restrictions on this pre-processing step. So, one of them was it has to be injective. Okay. So, assume that all these things are maintained and then we can actually extend this x with pad x, and then what is the size of this y? Y is a fixed multiple of t. Okay. So, therefore, it is RT where R is some integer value. Okay. So, now consider any w value which is any arbitrary bit string and form an x dash such that x dash is nothing but x appended with pad x. Okay. So, that is the previous thing and then that is appended with w, right. So, here what is the value of corresponding value of y dash? So, y dash, what you do is that you take this and you append this with the corresponding padding of x dash. Okay. So, therefore, you take x, append that with pad x, append that with w and append that with pad x dash. Okay. So, what is the size now of this particular y dash? It is some r dash t, where r dash is obviously greater than r because it is a bigger message, right. So, now note that since r value is known, I can actually do this. I know that when I in the first query what the attacker has obtained is that he has asked for the corresponding MAC of x, right. So, therefore, what he has obtained is x and also hkx. So, hkx is nothing but zr. So, zr is, suppose that z is an iterative output, I mean you compute the you remember the Markle-Damgard's algorithm. So, each step it was generating one z value. Okay. So, therefore, after the rth step whatever you obtain was the message was the MAC of x, right. So, the question is that now I am interested in computing zr dash, right. So, zr dash is quite easy because you know that zr plus 1 I can do like compress, then the next thing will be hkx appended with yr plus 1. Okay. So, then you can again continue with this step and similarly you can obtain. So, if you continue with these steps you can obtain the value of zr dash. Okay. So, you see that compress of hkx appended with yr plus 1, compress of, so you obtain zr plus 1. Now, you take zr plus 1 and append that with yr plus 2, because all these values are known to us, and then from there you obtain zr plus 2, and again take zr plus 2, append that with yr plus 3 and obtain the value of zr plus 3. So, continue in this fashion, you will obtain the finally the value of zr dash, right. So, therefore, you see that hkx dash is now equal to zr dash, and again what we have seen is that we have actually not used the knowledge of the value of key. What we have used is actually a message value and a previous MAC construction. Okay. So, therefore, you see that this is actually not so good. So, therefore, we need to do something different from this. Okay. So, first of all, in order to understand what we should do, we have to define what is the notion of security. Okay. So, that we have done for our previous cases like block ciphers, team ciphers and other things. We will continue with that approach and define what is meant by security. Okay. So, therefore, the idea is this, that the attacker is suppose allowed to request the valid pairs for any queue messages. Okay. So, therefore, what the attacker does, he obtains a list which is of the form of say x1, y1, x2, y2 and so on till xq, yq. So, all of them are these y1, y values are actually are the valid MAC values for the x values. Okay. So, therefore, y1 is nothing but the MAC of x1, y2 is the MAC of x2 and yq is the MAC of xq under a given key. Okay. So, note that the attacker does not know the corresponding key value, but he has just asked the oracle certain MAC values and the oracle has responded with these MAC values. Okay. So, now the question, or rather what we call as forgery is this, that if he or she is actually able to output x comma y, where x is not among the q values queried for, then we say that the pair is a forgery. So, therefore, the idea is that from these previous q values, if the adversary is able to generate another valid pair, okay, so I call that x comma y, where x does not belong to x1, x2 or so on till xq, then the attacker is said to have actually created a forgery. Okay. And you understand that this can have a probability, and the probability, if this probability is epsilon, which means if the least probability of this event is epsilon, okay, or the probability is at least epsilon, okay, then the adversary is called an epsilon comma q forgery. So, therefore, it is called epsilon is the least probability of success of the attacker and q is the number of queries which he has asked for. Okay. So, again you note that in order to have a very practical forgery, then this q has to be small, right. If this q is exponentially large, then obviously that is not a practical attack, right. So, therefore, this has to be polynomial in terms of the input size. Okay. Okay. So, therefore, now let us try to understand how we can actually obtain a MAC, a proper MAC function. Okay. So, for this let us assume certain things. Suppose that you have got two hash families, you know what is a hash family now. So, suppose you have got two hash families G and H, and the domain and range of G is x and y and the domain of H is y and z. Okay. And the key value of G is k and the key value of H is L. Okay. So, these are two hash families. Okay. So, now consider the composition of these hash families, and therefore, the hash family composition would be x, and from there you map that to z. Okay. So, it is x comma z, and the corresponding key is denoted by m, and the composition is denoted by G composition H. Okay. So, you know this composition is a same thing as that we do for functions. So, therefore, how is m defined? M is the Cartesian product of k and L. Okay. So, you take k, which is the key of G, and you take the key of H. So, these are two keyed hash functions actually, and the corresponding key value m is the simple Cartesian product of k and L. Okay. So, how is G composition H defined? So, G composition H is defined as, first we take from this G, we choose arbitrarily a function small g, and from H we choose arbitrarily a function small h, and then first we apply G k under a given key, and then apply H under a given key L. Okay. So, therefore, this is how the composition is defined. Okay. And this we do for all possible x values. Okay. So, you note that this is actually another key hash function whose key is L cross k or k cross L. Okay. And what is the corresponding domain and range? The domain is x. Okay. And you map that actually to z, right. So, you take x, and from there you transform that to y, and from take y and transform that to z, right. So, therefore, that is a final mapping. So, the idea is this, that is the result is that this is called the nested MAC or the NMAC, and this nested MAC is secure provided that the following two conditions hold. What are the two conditions? The first thing is that H is a secured MAC given a fixed unknown key. Okay, so, therefore, H is the outer MAC, if you remember, we sometimes call it the little MAC. So, this little MAC is actually secured MAC given a fixed unknown key, and G is actually a collision resistant hash function given a fixed unknown key. Okay. So, given a fixed unknown key means the key is actually in this case unknown. Okay. So, you remember the original collision resistance or collision problem in case of unkeyed hash functions. So, this is actually a harder problem from the point of view of the attacker, because the attacker does not know the corresponding key value also, right. So, in case of normal hash functions we knew the description, right. So, therefore, we could have taken analytic methods to find out the two x values which collide, but in this case that is something which I do not know also. I mean, there is another thing, like for example, I do not know the corresponding value of the key k. Okay. So, therefore, if this is a keyed hash function, to compute two x values which actually collides under gk is actually a harder problem than a normal collision attack. Do you follow what I am saying? What I am saying is that suppose in case of the normal hash function collisions there is no key, right. So, therefore, you know the algorithm. So, therefore, you can actually do a lot of pre-processings and analytic technique, apply a lot of analytic methods, and from there you can actually find out two x values which will collide. But in this case you have a bigger problem because you do not know even the value of the key. Okay. So, this is actually a, you can say that this is actually a harder problem from the point of view of an attacker. Okay. So, therefore, this is the corresponding composition function, and what we said just now is that if this particular composed function has to be a good MAC function, then this gkx has to be a collision resistance under unknown key. Okay. And HL or the little MAC has to be also a good MAC. Okay. And therefore, this is actually the, so therefore, if these two assumptions are maintained, then the nested MAC is also secured. That is the idea. Okay. So, let us try to understand this. So, for this we will actually define three kinds of adversaries. Okay. So, the first kind of adversary is something who forges the nested MAC or the big MAC attack. Okay. So, therefore, assume that there is an attacker who actually attacks the nested MAC. Okay. And assume that there is a small MAC attack which actually does forgery for the little MAC. Okay. And there is also assume that there is another collision finder for the hash when the key is secret. The key is not known to the attacker, and suppose there is an attacker who is still able to find out the collision for the hash. Okay. So, this is called the unknown key collision attack. So, if you assume these type of these three attackers or these three attacks, then actually you can relate the probability of success of these attacks. Okay. So, we will try to understand how. Okay. So, let us see how.
So, the definition of composition was G composition H. So, shouldn't H be applied first? Which one of them is big?
G composition H means G is applied first. So, if you go back and just check your discrete maths book, it is like that only. F1 composed F2 means that F1 will be applied first and then followed by F2. Okay, it is not the other way around. It is not F1 dot F2, it is F1 composition F2. So, F1 will be applied first and then F2. Okay. So, let us any doubts about this? Okay, let us assume this for our class. Okay, so there is nothing. Okay, so therefore, let us try to create an attack for this particular MAC. So, how will I approach? So, you know that how we have approached till now. So, by now I think we have a proof idea, right. So, one easy way of starting would be, let us assume that there is an attacker against this composed hash function. Okay. So, consider that or assume that there is no attack against I call it the little mac, okay, with probability of epsilon 2. Okay, so yeah, I call it epsilon 2 because to maintain my 1 second. Okay, so suppose that assume that there is no attack against the little mac with probability of epsilon 1. So epsilon 2 I have called it because assume that there is no collision finder algorithm, okay, with a probability of epsilon 1. Okay. So assume that there are no such algorithms with probability of epsilon 1 and with probability of epsilon 2. So which means that if there is a collision finder algorithm, then the probability of success of the collision finding algorithm will be lesser than epsilon 1, right. So assume, so if there is such an algorithm, then the probability of this collision finder algorithm, okay, the probability of its success will be actually epsilon 1 minus some x1 value. Okay. So assume some x1 is greater than equal to 0. Okay. So the probability of success of the little mac would be also equal to epsilon 2 minus x2, where x2 is greater than equal to 0, right. So also assume that there is now an attacker against the Big Mac. Okay. So assume that there is an attack against the Big Mac. Okay. So therefore let the probability of success of the attack against the Big Mac be at least epsilon. Okay. So that means the probability of success of the attack against Big Mac equal to epsilon plus x, where x is greater than equal to 0, right. So if there is such a kind of attack, okay, and suppose the number of queries which is required equal to q, okay. So which means that the attacker in this case can ask for x1 values till xq and obtain the corresponding z1 to zq values, right. So from these pairs the attacker is suppose able to find out or return two corresponding values, say x comma z, okay, which is valid, right. So therefore x comma z is a valid pair, therefore it is an attack, right, under my definition of security, notion of security. Okay. So x comma z is a valid pair, right. So
all these max have been using a single key, right?
Yeah, that is under the assumption, right. So therefore assume that all of them, all the keys are same. Okay. So you take x1 to xq and you obtain z1 to zq, right. So then what you do is that you take this. So now what you see is that suppose x comma z is a valid pair, and if you consider this particular algorithm like x1 to xq, so therefore if you consider the collision finding algorithm, so suppose what it does is that it asks for the corresponding values of or corresponding hash values of x1 comma xq and also of x. Okay. So this is my collision finder algorithm whose probability of success is given by epsilon 1 minus x1. Okay. So how many queries has this algorithm made for? Q plus 1 queries. Right. So now what you do is that you obtain the corresponding hash values, like collision finder algorithm means what? It will give you the corresponding hash values. So it will take this and apply the corresponding function which was defined by gk, right. So it will apply gk over all these values and obtain y1 to yq and also y, right. So now the objective of the collision finder algorithm will be to predict a collision from these q plus 1 values. Okay. So now note that if this collision finder algorithm is successful, okay, then I mean note that there can be two cases. Okay. So one case is where y, okay, I call that case 1, is where y, okay, belongs to y1 to yq. Okay. So if y belongs to y1 to yq, then obviously you can take that corresponding yi value and also y value and report them as two collisions, right. So that means in that case the collision finding algorithm is successful, right. There can be another case which is case 2 where y does not belong to y1 to yq. Okay. In that case you see that y is not a corresponding collision value. Okay. So but you note one thing, that since you know the corresponding values of z1 to zq, okay, so in that case you know a corresponding y value and you also know the corresponding z value of that. So that means that you can, in case 2, so case 1 is an attack against gk or the collision resistant part, and case 2 is an attack against the little mac. Why? Why is case 2 an attack against the little mac? Because what is the objective of the little mac attacker? It will take y1 to yq, okay, and ask for the corresponding queries, corresponding outputs. Okay. So what are the corresponding outputs for y1 to yq? It is z1 to zq, and it also knows y and it also knows z, because it knows z from the previous attacker's output, right, or from the previous oracle's output. So now you see that y does not belong to any one of y1 to yq by this case, right, under this case, right. So that means now this attacker can actually report y comma z as a valid pair, right, and y is a different input message. So therefore you see that this is an attack against the little mac. Do you see that? Shall I repeat this? Okay, so you see that what is the idea? The first idea is that you take x1 to xq, okay, and you obtain z1 to zq. So these are all the corresponding MAC outputs of the composed function, composed MAC. Okay. So you see that x comma z is a valid pair under the assumption that the composed hash function is an attacked hash function. Okay, attacked MAC. So now you take this collision finder algorithm and tell it to ask for q plus 1 queries. So therefore you see that x1 to xq and also x. So therefore there are q plus 1 queries. So you obtain y1 to yq and also the value of y. Okay. So now there can be two cases where y belongs to y1 to yq. If y belongs to y1 to yq, then the collision finder algorithm is successful. But if y does not belong to y1 to yq, then what I am trying to justify is that this is an attack against the little mac. Why? Now because it already knows x1 to xq to it, I mean it knows z1 to zq, and we know the value of z, right. So therefore we also know the corresponding MAC output of y, right, and now y does not belong to any of the y1 to yq values. So therefore now this is, if you consider the attack against only the little mac function, then you have got actually a valid pair y comma z where y does not belong to any of the previous queries to the oracle, right, and therefore this is an attack against the little mac function, right. So now if I try to justify that, what is the probability of success of the big Mac attacker? It was epsilon plus x, okay, that is equal to epsilon 1 minus x1 plus epsilon 2 minus x2, because any of the two cases can occur, okay. And therefore from here I can justify that epsilon will be lesser than epsilon 1 plus epsilon 2, because all the x1 values are positive values, positive or greater than equal to 0.
So the composed functions are basically known to the composed hash function known to the attacker.
The composed hash function is known, but the key is not known.
So okay, the key is not known. So can't we take any arbitrary message and just use the function, get the corresponding hash?
No, but the thing is that
Yeah, so here 2 to the k1 and 2 to the k2 possibilities.
yeah, but that is a, so again we told that we require to make q small for that. I mean, definition wise you have to make polynomial number of queries, you have to make small number of queries. So for example, if I make, again the problem comes in terms of computational security, right. So what do you have, what you can do in today's day, right. So do you follow the idea behind the proof? So now this is threaded in terms of a theorem. It says that suppose x, z, m, g and composed with h is a nested MAC, and suppose that there does not exist an epsilon 1 comma q plus 1 collision attack for a randomly chosen function gk. Okay, so you see y q plus 1 now. Okay, when the key is k is secret, for the suppose that there does not exist an epsilon 2 comma q forger for a randomly chosen function hl which belongs to h, where L is a secret. Finally, suppose that there exists an epsilon comma q forger for the nested MAC for a randomly chosen function of composed function, then actually epsilon is less than equal to epsilon 1 plus epsilon 2, right. So that means that if you can give guarantees for epsilon 1 and epsilon 2, then actually you can give an upper bound for epsilon, right. And that is the idea, that if you can make your g function a collision resistant against an unknown key attack, and if you can make your h function also I mean make it a secured MAC, okay, under the secured key MAC, then your nested MAC is also secure, right. So this is the idea of this proof. Okay, this was given by Mihir Bellar and his colleagues. So this is a quite interesting result. Okay. So this was actually used by Phipps to make something which is called an HMAC or a hash based MAC. Okay. So I will just go through the description of the HMAC. So it is as follows, that is, it constructs a MAC from an unkeyed hash function, namely you can take SHA-1 for example. Okay, I have taken SHA-1 because we have seen more or less what is a SHA-1 function. Okay. So in case of this, that is, you take k which is a 512 bit key, and suppose x is the message to be authenticated. Here there are two constants which are taken, it is called IPAD and OPAD. Okay. So IPAD is called because it is inner pad, and OPAD is called because it is outer pad. Okay. So that is nothing, it is just the way the nomenclature works. Okay. So these are all 512 bit constants, and the description is as follows, that IPAD is actually 3636 repeated actually, and OPAD is actually 5C repeated. So these are some constant values. Okay. So how you can start is like this, that therefore the 160 bit MAC is defined as follows. You take k and you XOR that with IPAD, you append that with the value of x, apply the SHA-1 function, again append this with k XORed with OPAD, and again apply SHA-1 function. Okay. So you see that here you require to apply multiple times the compressed function because x can be arbitrary. Okay. But here for the outer hash function or outer SHA-1 function, only one application of the compressed function is necessary, because this reduces it to 160 bits, and this is actually a 512 bit output. So therefore the compressed function, which is something, if you remember the SHA-1 description, takes 160 plus 512 bits and gives you a 160 bit output. Okay. So therefore this is a 160 bit message digest for x. Okay. So this is quite simple description, and how many times will you take 36 depends upon the parameters of SHA-1. So in this case, for example, k XORed OPAD, suppose k is a 512 bit value, then obviously 36 is what, 8 bits, right. So therefore it is 512 by 8. So I think it is how much, 64 times you have to repeat this value of 36. Similarly 5C also. Okay. So why 36 and why 5C, you can just justify. So these are some thumb rule values. The idea was that to make the number of differences from 36 to 5C as large as possible, so that after that they believe that the SHA-1 function will take it and will actually increase the diffusion of this difference. Okay. So these are some just two arbitrary values which are taken. Okay. So, this is an illustration. What you do is that you take k, and from there you can just XOR that with the iPad value, okay, and then you can append that with x value, and then you can actually apply the hash function. Okay. Then what you can do is that you can take k XOR with OPAD, and both of these things you can actually append. You are appending both of them, and then finally you are applying the hash function. Okay. So, this is pictographically how you are obtaining the corresponding HMAC output. Okay. So, the security arguments are like this briefly. The first application of SHA-1 is assumed to be an unknown key collision resistant. Okay. So, this you follow from the HMAC construction, right, that the assumption is like this, that is the first application of the SHA-1 is assumed to be an unknown key collision resistant application. The second application is assumed to be a secured MAC. Okay, and second SHA-1 actually needs, I have already told you, and therefore, under these two applications or rather under these two assumptions, the composed HMAC is also a secured MAC. Okay. So, note that the extension attack which we have seen in the previous case is prevented in case of NMAC or HMAC, because the outer HL is actually avoiding the or stopping the exposure of the inner GKX output. So, the previous thing that we have seen, I mean, the attack against iterated MACs where we made the IV value secret will actually not work in this case, because here the outer hash function or the outer application of the hash function which is denoted by HL is actually stopping or avoiding the exposure of GKX to the attacker. The attacker is not now getting the value of GKX, so that he can actually append and generate a corresponding message, right. So, therefore, this is the way how it is stopped or inhibited. Okay, then we will conclude today's class with a construction which is called a CBC-MAC. So, CBC, all of us know what is a CBC by now, okay, cipher block chaining. So, what we do is that as follows. So, in order to compute CBC-MAC, you take x and you take a key value k, and this is how you do. So, therefore, you take x and assume that each of these x values, that is x1 to xn, all of them are of block length t. Okay. So, what you do, you choose an arbitrary IV value which can be all zeros, okay, and you make y0 as IV, and then you just apply the corresponding CBC function. So, what was CBC function? You take the previous yi minus 1 value, okay, XOR that with xi and apply the ek function, right, and this is an endomorphic block cipher. So, you know what is an endomorphic block cipher. So, therefore, you apply this ek function and you apply the value of yi, you keep on doing that for n number of times, and final value of yn values is something which you return, right, as the corresponding MAC of x under the key k. Okay. So, we will consider one attack against this particular CBC-MAC construction. Okay. Okay. So, the attack works like this. Okay. So, suppose you take q is approximately equal to 1.17 into 2 power t by 2, and that is the closest integer to this particular value. Okay. So, why we have taken this? Any ideas? Do you remember this value 1.17? Yeah, we obtained it from the birthday paradox thing, right. So, therefore, what you do is that you choose q distinct bit strings of length t, which you denote as x1 to x11 to x1q, and you choose q random bit strings of length t, which you denote by x21 to x2q. Okay. So, therefore, what is the difference between these two choosings is that you choose in this case q distinct bit strings, which means that there are no two pairs which are equal, all of them are distinct, okay, and then you choose arbitrarily q random bit string values. Okay. So, you note that q is approximately equal to 1.17 into 2 to the power of t by 2, right. So, you see that any of them are not, I mean, there are no pair which is equal in this case, right, because you have purposefully chosen all of them to be distinct, right. But what about this? So, you see that since q is of this order, there is a quite significant probability that at least you will find a pair which are same, right, right. So, therefore, now what you do is that you choose x3 to xn, and suppose that all of them are fixed bit strings of length t. Okay. So, from there, from these all these choosings, you actually start making or constructing messages of this form, say xi equal to x1 I appended with certain, I mean x2 I and appended with so on till xn I. Okay. So, and this you do for I running from 1 to q. So, how many messages do you form in this way? You form q messages. Okay. So, therefore, what you are doing is like this. You do xi and you take x1 I and you append that with x2 I, okay, and you append this, and this is xn I. Okay. So, that means that the first, if I consider I equal to 1, it will be x1 equal to x1 1 appended with x2 1 and so on appended with xn 1. Okay. Similarly, I can form for I equal to 2, I can form x2 equal to x2 1 appended with, sorry, x1 2 appended with x2 2 and so on xn 2. So, I can continue with like this, and up till I equal to q, I can obtain the qth message like x1 q appended with x2 q and so on xn q. So, you note that among all these messages, all these values are distinct, right. But here, as we argued, because of the order of q, there has to be two pairs which are equal. Okay. So, what are these things starting from x3 or rather x3 1 to x3 q. Okay. So, all these values are nothing as we chose from x3 to xn, we are just repeating those values. Okay. So, all these values are same, all these values are same, all these values are same. Okay. So, you see that if two messages are equal, then there is only one requirement, that the corresponding x2 I values need to be same, right. So, that means that if you find that xi is equal to xj, where I is not equal to j, so this is equivalent to saying that x2s are equal. So, that means x2i is equal to x2j, right. And we know that since q is of the order of square root of n or other square root of q, okay, or sorry, order of 2 to the power of t by 2, then actually we should find out one such pair with a quite large probability, the probability of approximately half, more than half. Okay. So, you see that the idea is that xi and xj not being equal to each other means that if I is not equal to j, then it means that x1i not equal to x1j. Okay. So, x1i and x1j are not same to each other. Okay. So, sorry, this will be actually x2. Okay. Yeah, because x1i is always equal. So, this will be actually x2i not equal to x2j. Okay. So, this is what I have written here. Okay. So, therefore, you can see from the written thing there is a mistake there. So, x2i is not equal to, I mean rather if x1i is equal to xj, then it means that x2i is equal to x2j. Okay. And if they are not equal to each other, this symbol indicates that x2i is not equal to x2j. Okay. So, the attacker now what he does is that the attacker queries the hash value of the q xi value. So, therefore, you take all the xi values and you ask for the corresponding hash outputs. Okay. So, now due to the birthday paradox, there is a collision with probability half or more than half actually. So, suppose that hkxi and hkxj are actually colliding. Okay. So, suppose that hkxi and hkxi collides. So, I call that hkxi and hkxj are colliding. So, what does it indicate? If hkxi and hk, so you understand why hkxi and hkxj will collide, because of the birthday paradox, right. So, what does it mean? So, in this case, this happens if and only if, no. So, if you see that CBC construction, the messages are formed in the form that from x3 onwards all the messages are same, right. The input messages, that is the first block, are different, all of them are distinct. The second part can be equal or may not be equal, right. So, suppose what happens is that, so therefore, this happens, okay, if and only if y2i and y2j are same. Okay. So, what is y2i and what is y2j? So, y2i is equal to y2j. So, you come and you just see this, y2i is equal to y2j. Okay. So, what does, because after this all of them are, I mean if these two values are same, then after this subsequently you are again applying this to the CBC chain, right. So, therefore, just chain wise you take this and you can, I mean the rest of the input messages are same from x3 onwards till xn, all the messages, all the I values has got the same value, right, all of them have got the same value. So, therefore, this collision, that is hkxi equal to hkxj, happens if and only if y2i is equal to y2j. Okay. So, what is y2i and what is y2j? You know that y2i equal to y2j implies that this is nothing but ek, okay, applied over, it is applied over x2i XORed with y1i, and this is ek with x2j XORed with y1j. Okay. Right. So, these two values are same, right. So, suppose in that case, since your ek function is an invertible function, so what does it indicate? It indicates that x2i XORed with y1i is equal to x2j XORed with y1j, right. So, that means that x2i XORed with y1i is actually equal to y1j XORed with x2j, right. Is it, till this part is clear to us? Yes, clear to us? Okay. So, now you see that actually you have obtained the corresponding so many MAC values. So, now you consider that x delta is some non-zero bit string of length t. Okay. Suppose x delta is some non-zero bit string of length t, which I know. Okay. So, then you can define v as like this. So, you know that I and j values, I mean you already know the corresponding I and j value for which the collision in the hash output has occurred, right. So, you take the corresponding xi value and from there you actually make this v message. How? Now, you keep rest of the things same, only the second message you take x2i XORed that with x delta. Okay. So, now you ask for the attacker asks for the corresponding MAC of v. Okay. Now, from v you can actually make a w which is nothing but only the x2j value is XORed with x delta, right. So, now you note one thing, that the MAC of v and MAC of w are same. Why? Because of this particular requirement. You see that what is the requirement? The requirement is that x2i XORed with y1i, okay, equal to x2j XORed with y1j, right. So, now you assume that if I just take x2i XORed with x delta here on left hand side, okay, then also this holds, right. So, therefore, this equality is not disturbed, right. So, therefore, you see that if I form a message with these two as the second block, still my equality of the hash function is maintained, right. So, therefore, you see that the MAC of v and the MAC of w are same, okay. But are v and w same? No. So, that means that if I have queried for the MAC of v and I report the MAC of w, then actually I have formed a valid pair, right, because v and w are not the same, but I know the corresponding MAC value. Okay. So, how many queries did I do? How many queries did I do? I mean I did the queries for how many values? I did q plus 1, but the order is 2 power t by 2, and what is the probability of success? half. So, that means what we have done is that we have made a half O 2 to the power of t by 2 forger. Okay. So, that follows from the Birthday paradox. Okay. So, you see that the Birthday paradox has got lot of applications in cryptography and cryptanalysis. Okay. So, a simple stating algorithm, but it has got huge applications. Okay. So, you see that so therefore, now we know the corresponding MAC values and we know corresponding valid pair values. Okay. Okay. So, I will just ask again, give you certain points to think on. So, for example, what would have happened if the hash function g in the NMAC construction would have been unkeyed, for example. So, for example, in the NMAC construction we have assumed that both the hash functions are keyed. So, assume that the g function was an unkeyed hash function. Okay. Would the security have, I mean, what would have been happened to the security of the construction? You can just think on this, and also you can think on why are different IPAD and OPAD values used. Okay. I mean, can I keep IPAD and OPAD same? Okay. And just think on this. So, I followed from mainly from Stinson's book, and certain interesting things you can find from this paper also, keying hash functions for mastery authentication, published by Bellar, Canetti and Krozik. And next day we will continue with more number theoretic results, and we will actually start asymmetric cryptography from next day.